Hi guys, it's your science teacher here, back with another video. This time I'm going to go through all my predictions for chemistry paper 2. If you've watched my other videos, you will know that these are just predictions and I only go through the topics that it says is going to be a key topic from the advanced information on the AQA sheet. And because of this, I do advise that you do watch my full topic videos as well as watching this video. But without further ado, let's get into today's video. Let's start off by looking at where I got my information from, and it's from all of the AQA advanced information. So if you see it has information on what required practicals will be assessed, it also says some of the things that will not be assessed in this paper. But what I'm going to focus on is I'm going to focus on the things that are going to be assessed in this video. And let's start off with the required practicals, because I think that this is a really easy way to pick up easy marks, because we know it's definitely going to be in the paper, and there, with the required practicals, there's only a certain amount of information they can really ask. So the first required practical is a rate of reaction practical, and it says investigation for how changing the concentration can affect the rate of reaction. And there is two practicals this kind of fit this specification. The first one is by measuring the volume of gas produced in a certain amount of time, and the second is by looking at a precipitation reaction. So let's have a look at the volume of gas one first. And to measure the volume of gas, here we've got a gas syringe. We also have a delivery tube from a conical flask where a reaction will be happening, and this reaction will be bubbling up and emitting a gas. Now, what we'll notice in this practical is that as time progresses, what will happen is the amount of gas produced in the reaction will slowly increase, and we'll end up getting a graph that has a shape something like this. Now, we're going to talk about why we have this shape of graph now. It's because of the fact that during a reaction, the reaction over time is going to start to slow down. And in fact, when we got this point on my graph here where it's flattened out, my reaction has in fact stopped. And there's a reason why reactions get like this, and that's because of the fact that we have made now all of the product and we have no more reactant left in order to react together. So our reaction has come to a stop. Here I've just drawn an example of a reaction in which I would produce a gas. So here I've got magnesium, I'm reacting it with hydrochloric acid, and I'm making magnesium chloride and hydrogen. Now, because of the fact that they said that we can change the concentration, we're going to have a look at the effect of what changing the concentration of our hydrochloric acid will do to the rate of the reaction. Now, what should be observed is if the concentration is less, then the rate of reaction will be less. And what you should observe is you should observe a line in which it's not as steep, but our reaction will eventually stop, just like the first one. So you'll get the same shape graph, but it won't be as steep for less concentration. So this could be a 1 molar solution, and this one here could be a 2 molar solution of hydrochloric acid. Now, the reason for this increased rate of reaction is due to the fact that there's going to be more particles that can collide with one another, and that's going to increase the rate of reaction. And that's just simple collision theory, which we'll go into more detail in the rest of the video. But just before we do move on, I just want to go just quickly into a definition for what we actually mean by rate of reaction. And that's just the amount of product we're making in a certain amount of time. It could be the amount of reactant used up, but in this reaction where we're making a gas, we're going to be measuring the amount of product made in a certain amount of time. And as you can see by them two graphs, this one, the blue line, which is more concentrated, is making product at a much faster rate. Therefore, it has a faster rate of reaction. Now, you can also find the rate of reaction at a certain point by drawing a tangent to the line, and we call this the instantaneous rate of reaction. So if I look at my 2 molar rate graph, if I want to find the rate of reaction at, say, for example, 20 seconds, because it's not going to be the same rate of reaction all the way through my reaction because of the fact that the amount of reactant is changing, isn't it? So the reaction is going to get slower over time. So what you need to do is you need to draw a tangent to the line. And what I mean by a tangent is a line which is going exactly the gradient at that point of the graph. So you're going to put your ruler on your page and you're going to draw a triangle on your page, and you're going to do the change in y divided by the change in x in order to get your instantaneous rate of reaction. In terms of safety precautions for this practical, remember that you are working with acid, so you are going to have to make sure that you wear goggles at all times, and that's an easy safety precaution to remember for any practicals that involve chemicals. The next way to measure the rate of reaction is if we do not have a gas coming off, but in this example of reaction, we have a precipitate reaction. And what we're going to look at is sodium thiosulfate and hydrochloric acid. Now, this is a reaction you will have done in school. However, it's not the only precipitate reaction out there, so they could throw in you as a bit of a curveball, maybe do a different reaction, and you've got to notice that you are making a solid product. In this case, a sulfur is the solid product, and that is why you get a white precipitate in this reaction. Now, in this reaction, you could either change the concentration of sodium thiosulfate or hydrochloric acid. It doesn't really matter which one you change, as long as the other one is the control variable. And what you're also going to have to control is other factors that could affect the rate of reaction, for example, the temperature. If you increase the temperature, that's obviously going to have an effect on the rate, speeding it up. Now, if this is the practical out of the rates that they choose, then there is a clear and obvious error in this practical that they probably will ask you about. And it comes from the fact that when you have a precipitate reaction in a disappearing cross experiment, what happens is you place the cross under the conical flask and you wait for it to disappear. Obviously, the longer it takes to disappear, the slower the rate of reaction. However, if I look at the disappearing cross and one of my friends looks at the disappearing cross, we may get different times. And that's because in this practical, the main error is the fact that there is not really a clear end point for the reaction. This means that people will get varied results, and this is obviously not very good if you want very accurate data. And of course, what you can do is if you want to make these results more reliable is to take repeat readings yourself. And if you want to make your results repeatable, let someone else do it and see whether they get the same results as you. The next required practical is looking at identification of different ions. And we're first going to look at my favourite practical in the GCSE Chemistry syllabus, which is identification of metal ions using flame tests. And the way to carry out a flame test is first you're going to need some nichrome wire. This is what we are going to put into our Bunsen burner, and we need to clean our nichrome wire using an acid. Usually we use HCl in order to clean our nichrome wire. Then we're going to place our wire into the flame, and now it's ready for our sample. The reason why we have to clean our nichrome wire is it might have some metal remaining from the last time we've done a flame test. So now we've placed it in the flame, we are ready to add sample to the nichrome wire and place back into a blue flame. Now, depending on which metal ion is present will depend on which color you will get. So if we have lithium ions, we will expect a red color. Sodium will produce a yellow flame. We will get a orangey red flame if we have calcium present. We will get a lilac color if we use potassium. And finally, if we get a blue color, we know that we have copper ions present. Now, flame tests are useful if you only have one metal ion present in your solution and if your metal ion gives out a colour when it is heated in a Bunsen burner. However, what happens if we don't have a metal ion which gives out a colour when we heat it in our Bunsen burner? Well, we're going to have to use another identification tool. If you don't make a clear colour when you put your metal ion in a Bunsen burner, then what you can do instead is add sodium hydroxide to your metal containing compound and see what colour precipitates that you get. Now, the key thing with this practical is to make sure you only add a little bit of sodium hydroxide the first time you add this, because of the fact that aluminium can be distinguished from sodium and magnesium because of the fact it will dissolve if you have excess sodium hydroxide added to it. In addition, you can separate your magnesium from your calcium. Magnesium makes a white precipitate, whereas calcium also makes a white precipitate, but calcium also has a coloured flame. So we could revert back to our flame test and we could use our flame test to distinguish between our calcium and magnesium compounds. Also, if you look down here, I've used Roman numerals to indicate the charge on some of these ions. Here I have iron 2+, which has the iron with the brackets of the Roman numerals 2, and here I have iron 3+, and you'll notice that the different oxidation states of iron make different coloured precipitates. That's why they sometimes like to ask a question containing these two to try and fool you, and just be careful that you learn that these two ions of iron produce different coloured precipitates. We can also do tests to identify negative ions that are present as well. And there are 3 negative ions in which we need to know the test for, and the first one we'll look at is the one in the center. This is the test for the carbonate ion, and that's CO3 2-. And what we need to do for a carbonate test is we need to add hydrochloric acid to what will probably be a metal carbonate, and what will happen when I add hydrochloric acid is bubbles of carbon dioxide will form, and what I should see is my carbon dioxide will turn my lime water cloudy. The next one I'm going to look at is the test for the halides, and there is 3 results for this test that you just have to remember, unfortunately. And the way to test for a halide is we add some nitric acid and we also add some silver nitrate. What we get is we actually get a silver halide precipitate produced in this reaction. So here, if I'm testing for chlorine, I get a white precipitate, and this is caused by my silver chloride. So I'll just put AgCl just to help you remember that. Then here I have a cream precipitate, means that I have a bromide present, and my cream precipitate is silver bromide. And then if I get this yellow precipitate, this is my favorite color here, then I have silver iodide. The last ion test you need to know is the test for the sulfate ion, which is SO4 2-. Now, what we need to do to test for our sulfate ion is we need to add barium chloride, and we also will catalyze this reaction by adding some hydrochloric acid. Now, sometimes they do try and fool you and they say, why can you not use sulfuric acid? And you've just got to know that sulfuric acid already contains that SO4 2- ion, which will create this white precipitate here. And this white precipitate is barium sulfate. Now, that's what this reaction produces when you have a compound that contains a sulfate ion. Now, I know that it seems like you have a lot to remember for these practicals. However, a lot of this information is just regurgitating that information. So if you learn your reagents, you learn your color changes, you should be absolutely fine if one of these comes up. Final required practical that I'm going to talk to you about is chromatography and calculating the RF value of a spot that's moved up on our chromatography paper. Now, this is a required practical on the foundation paper. However, it could come up on higher tier later on, maybe not asking about the required practical, but just asking about chromatography in general. So the way to calculate the RF value is you need to do the distance moved by the spot divided by the distance moved by the solvent. So if we have a look, for example, at spot X, the way to work out an RF value is always go from the center of the spot. And if this has moved up 2.6 centimeters and my solvent has moved up all the way here 5.4 centimeters, then what I would do to calculate my RF value is do 2.6 centimeters divided by 5.4 centimeters. That gave me an answer of 0.48, and you can always kind of check that you've got it the right way round with RF values, because your answer should always be less than 1. Now, the reason why the different spots separate is due to their different solubility in the solvent. Here you can see that Y is clearly more soluble than X. This means that it's travelled further up my chromatography paper, which is also called the stationary phase. Now, it's always important to remember as well that different solvents have different solubilities. So if you want more separation, you could just use a different solvent. Also, from visual analysis of chromatography, you can see what different compounds are in different substances. So here you can see that some of the spots align for some of the different components. Here in A, you can see this X here, it lines up with one of the components that's in B. That means that it probably is made up of some of the same stuff. Also, you can see that C is made up of 2 components, B is made up of 3 components, and A is made up of 2 components. Now that's all on the required practicals. Let's get down to a bit of content now. Now we're on to the actual content of the paper. We've looked at the required practicals. Let's look at the first topic and investigating factors that will affect the rate of a reaction. And we are going to first look at a theory called collision theory. And what collision theory states is that if particles do not have enough energy to react, they will not react together. Basically, there needs to be enough collisions with enough energy in the right orientation. And remember, the minimum amount of energy to start a reaction is called the activation energy for that reaction. So let's have a look at a few factors that can affect our rate of reaction. And the first is temperature. Now, if I just draw some particles here and if they are all moving around in random directions, I've got a little bit of a gas rocking here, then if I increase the temperature, what's going to happen to them particles? Well, they are going to move around a lot faster with more kinetic energy. Now, because they are moving around faster, they are more likely to collide and therefore more likely to react. So temperature is one way I can increase the rate of reaction. Another way that I can affect the rate of reaction is to change the concentration. The more concentrated a solution is, so if I increase the number of particles, the more likely those particles are to collide. So concentration is a key factor in increasing the rate of reaction. Another way I can increase the rate of reaction is to increase the pressure. So here I've got the particles and they are all spread out moving in random directions, but imagine if I make this box smaller by increasing the pressure, making them all have to occupy less volume, then the likelihood is those particles are going to hit into each other in the correct orientation and react. And then finally, what I can do to affect my rate of reaction is make a larger surface area. Now here I've drawn 5 quite large particles, and down here what I'm going to do to represent that this is a bigger surface area is draw 10 smaller particles. Now these 10 smaller particles would all fit into them 5 larger particles above. However, they have a much larger surface area. There's more surface where our reaction can take place, and therefore it's more likely to be a quicker rate of reaction. There is one other factor that can affect the rate of reaction which has nothing to do with collision theory, and that is by using a catalyst. Now, if I look at a reaction profile for an exothermic reaction here, and you can see the reactants have a higher energy than the products. Well, if I look at what a catalyst does, well, a catalyst actually lowers my activation energy. And because of this lowering of the activation energy and offering an alternative way for the reaction to go with a lower activation energy, then the reaction happens at a quicker rate. Now, catalysts are great because they do not get used up in the reaction. In addition to this, if you use a catalyst, maybe you don't have to use as extreme reaction conditions, for example, really high temperatures and pressures, so they can actually make your industrial process cheaper. However, catalysts do have a couple of disadvantages. For example, they are often quite precious metals that they're made of, so they're in limited supply. Sometimes they can be quite expensive as well, and different reactions require different catalysts in order to speed them up, so they can be quite specific to the reaction. What we're now going to look at is a special type of reaction called reversible reactions. And these are reactions that can happen in 2 directions. And you can tell that a reversible reaction has occurred if you see this double-headed arrow that you see here. This arrow means that the reaction is reversible. Now, there is a couple of examples of reversible reactions that your teachers have probably gone through with you, and this is probably one of them. Here you can see that I have hydrated copper sulfate, which is blue in its natural form. However, when you heat up hydrated copper sulfate, what you notice is that it becomes this white color, and the reason why it goes white is because it becomes anhydrous copper sulfate, and this is a reversible reaction. The forwards reaction we can call endothermic because it requires heat. It's taking in heat from the environment. You need to use a Bunsen burner. Then the reversible reaction, when I add water back to my copper sulfate, that's exothermic. And it's really important if you know that one of your double-headed arrows is exothermic or endothermic, the other is the opposite. They might not give you the colours of the different compounds here. They might just give you a word equation or a balance to symbol equation. So just something to look out for. If you have a hydrated compound, they put a bullet point and then they put the water after. This one, hydrated copper sulfate, actually looks like this. And then you've got your reversible reaction, and you're going to make your anhydrous copper sulfate. Anhydrous just means without water, basically. And to balance my equation, if there's 5 waters on this side, there must be 5 waters on this side as well. If you have a reversible reaction and you leave it for enough time, and you don't let anything escape, you have a closed system, you'll end up with where your reaction is making product as fast as it is going backwards, making reactant. And we call this dynamic equilibrium. Despite reaction going forward and backward at the same rate, you can alter conditions in order to move the reaction more forwards or more backwards due to a principle known as Le Chatelier's principle. And Le Chatelier's principle states that a reaction will try and counteract a change. This means, for example, if I was to try and increase the temperature in the reaction is going to try and decrease the temperature. If I was to increase the pressure, the reaction would try and decrease the pressure. And the way it can do this is by shifting the reaction to the right or the left to make more product or make more reactant. Now, this reaction here is in fact endothermic in the forward direction and it's exothermic in the backwards direction. So let's have a look at what will happen if I change the temperature of the reaction. So if I increase the temperature, what's going to happen? Well, my reaction is going to try and cool down. So what will happen is it will favour the product of nitrogen oxide here, so it will push the reaction to the right. And oppositely, if I decrease the temperature, what's going to happen with my reaction is it's going to push my reaction to the left as it's going to try and increase the temperature with an exothermic reaction. Now, as well as changing the temperature, I can also alter my conditions by changing the pressure. Now, the way to know what's going to happen in your reaction is to count the amount of moles of reactant or product. Now, here's a bit of a trick one for pressure, in fact. On this side of my reaction, I have 1 mole of nitrogen and 1 mole of oxygen, and they're reacting together to make 2 moles of nitrogen oxide. So in fact, pressure will not have much of an impact on this reaction. Now, what happens usually is that where there is less moles of product or less moles of reactant, they will be favoured if there's higher pressure, and the reason for that is because the less moles will occupy less space. So if I increase the pressure, it will shift to the side which has less moles. Another thing I can do is change the concentration of one of the reactants or products. Now, if I increase the amount of nitrogen, for example, then what my reaction is going to do is it's going to shift to the right to remove that nitrogen that I've just put in. On the flip side, if I removed some nitrogen from my reaction, then it would push my reaction in the direction to remake the nitrogen that I just removed. Now I'm going to do a bit of organic chemistry. Organic just stands for chemistry regarding carbon compounds. We're going to look at specifically hydrocarbons, which are carbons that are bonded to hydrogen. Now, we get a lot of our hydrocarbons from this mixture here, which is crude oil. And crude oil is mined from the ground, often deep below often quite deep beneath the sea, and it's made up of dead plankton and fish remains that have been there over millions of years, and over time have been compressed at really high temperatures and pressures and formed crude oil. However, in its pure form, it's not very useful. It's just a mixture of hydrocarbons, and it's an incredibly viscous liquid, meaning that it doesn't really burn very well, it's not very flammable, and it's very, very thick and not runny. So because of this, I need to separate my crude oil into useful components using a process called fractional distillation. And there's a few key principles behind fractional distillation. And basically, what fractional distillation does is it heats up crude oil to a really high temperature, causing it to evaporate. Now, when it's evaporated, it enters what's called a fractionating column. And this fractionating column is incredibly hot at the bottom, and it gets colder as you go up to the top. And because of this, the different hydrocarbons condense at different points in my fractionating column. My long hydrocarbons with a really high boiling point, they condense at high temperatures. My smaller hydrocarbons with a much smaller boiling point, they condense here, and after they've been collected, they can be used for their different functions. If you look at some of the different products from this fractional distillation, you can see that the large hydrocarbons such as bitumen is used in road construction, and basically it's not very flammable, so we don't use it as a fuel source. We get more useful hydrocarbons going up the fractionating column, as these are fuels that can be used in transport and natural gas for electricity. The reason for the different boiling points going from long hydrocarbons to small hydrocarbons is due to the intermolecular forces. If you have a really long hydrocarbon, then it's going to have more chance to have more intermolecular forces between the next long hydrocarbon, and this is what results in it having a higher boiling point. Now, they could ask quite a lot when it comes to organic chemistry, and we're just going to have a look at some of the key rules when it comes to naming some of these organic compounds, and we're going to have a look at their displayed formulas too. We'll first have a look at an alkane, and an alkane example is methane. Alkanes have the generic formula CnH2n plus 2, so you can always calculate how many hydrogens there are as opposed to the number of carbons. So if I look at methane, meth stands for 1, so there will be 1 carbon and there will be 4 hydrogens. And if I look at the displayed formula of what that looks like, I am going to show the bonds, because that's what happens in a displayed formula, and that's why it's different to a molecular formula. I think displayed formulas are more useful because they do show the bonds. However, in this displayed formula, I'm not showing actual bond angles, and that's a bit of a limitation of that model. Next up, I'm going to show you an example of an alkene, and an example would be ethene. Eth stands for 3, and if I look at the molecular formula for this, it'll be C2H4. That's different to a alkane because alkenes have the generic formula CnH2n. And if I draw out its displayed formula, this time it has a double bond. This is because we call this type of hydrocarbon unsaturated because it contains double bonds. And if I draw that out, still look at each carbon, it does have 4 bonds at each carbon, so I'm still following all the rules. The next functional group I'm going to show you is alcohol, which is propanol. Now, if you look at the prefix, that's prop, and prop has 3 carbons, and this time the functional group is OH, so it has all the hydrogens apart from it has an OH at the end. So if I times it by 2 and add 2, that would be 8. So it's going to be C3H7OH, as it's got to have a bond free for this OH functional group. And if I draw it out, I've got my 3 carbons, 1, 2, 3. I've got my OH, and then I fill my other carbons with hydrogen. Now, another example of a functional group is carboxylic acids that you need to know about, and I'm going to choose butanoic acid as my example. And if you get an example like butanoic acid, it's probably easier to draw the displayed formula before working out its molecular formula. So if I draw out my 4 carbons, there we go, and I put on my double bond OH functional group there, and now I draw my hydrogens in. Then all I've got to do at the end is count the number of hydrogens, oxygens and carbons, and in total I have C4, I have H, 1, 2, 3, 4, 5, 6, 7, 8, and I have O2. And that's fine to leave your molecular formula just like that. And then finally, the last functional group I'm going to show you is a ester, and I'm going to pick propyl ethanoate. Now, these are the hardest to remember which way round you've got it, and they're made from reacting an alcohol with a carboxylic acid. Now, my ethanoate group, that must be ethanoic acid that reacted, so I'll draw that bit first. I've got my double bond O here, and my ester link comes here. It's actually a condensation reaction because I make water as a byproduct here. And then I've got my propyl group down here, 3 carbons, lovely, and I fill up my carbons with the hydrogens, making sure all of them have 4 bonds, and that's how I kind of check whether I've done this right or not, is I count how many bonds each carbon has, and there I've drawn it on, and now I can work out my molecular formula. I've got in total 5 carbons. In total I have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and I have 2 oxygens. One of the main uses of hydrocarbons is to burn them, and the reason why we do this is in order to create electricity. We often use this in power stations, natural gas and coal power stations, which burn fossil fuels in order to generate our electricity. Now, if I get complete combustion, then I end up with the products of carbon dioxide and water. However, I have another option, which is incomplete combustion, and this is when I don't burn in plenty of oxygen and I have my fuel and I don't have enough oxygen. I could just say that this is a limited supply of oxygen, and this time I will make as my products carbon monoxide, carbon particulates and water. Now, this can be incredibly damaging because of the fact that carbon monoxide is a toxic byproduct of incomplete combustion. It binds to the hemoglobin in blood, and therefore your body cannot get enough oxygen. This is why in most houses there is a carbon monoxide detector. Carbon particles also, they are not great to have in the air because these are carcinogenic, meaning that they can cause cancer. And as well as cancer, they also can cause other respiratory issues. So you'll always know whether you've got complete or incomplete combustion by just looking at your products. Just remember that the formula of carbon monoxide, the molecular formula is CO, and the molecular formula of carbon particulates is just C. The next bullet point I'm going to talk to you is the composition of the Earth's atmosphere, and it's a kind of common misconception that people think that the Earth is mainly oxygen in the air that we breathe in, but in fact it is 78% nitrogen, and that makes up a key part of the air in our atmosphere. Then after that, the second biggest is we are 21% oxygen, and then The small branch, we have 0.9% argon in our atmosphere, and then the rest, so around 0.1%, is made up of other gases. And in that bracket, we have a bit of methane, carbon dioxide, and things like that. Now, the Earth hasn't always had the same composition of gases in its atmosphere. The Earth is 4.6 billion years old, and in its history, there has been many events that have changed the composition of the Earth's atmosphere. During the first few billion years, the atmosphere was only starting to form, and about 2.7 billion years ago, there was still a lot of volcanic activity, and these volcano eruptions put in gases into our atmosphere such as carbon dioxide, methane, water vapor, and ammonia. Now, over time, this water vapor started to condense, which formed our early oceans, and this was what fueled the next evolution of our atmosphere. Because of the fact there was water covering the surface of a lot of the Earth, microscopic organisms that photosynthesized could thrive in the water, and therefore they could put oxygen into our atmosphere. Now, because there is now oxygen on the planet, this allowed animals that respired to be able to live on our planet. Now, you might be asking where a lot of these gases went as well. Now, this carbon dioxide, that a lot of it was locked up in rocks and in the ocean. And the ammonia in our atmosphere, well, that reacted with the oxygen that was put in, and it made nitrogen, and it also made water as well. And nitrogen being so stable, that's why it is built up in such large concentrations in our atmosphere. We're now going to look at a specific reaction, a very important reaction in chemistry, in which we create a really useful product called ammonia, and it's called the Haber process. Now, ammonia is a key component to fertilizers, so that is why we need to produce it on an industrial scale. And what we do is we react nitrogen from the air with hydrogen, which is being collected from natural gas. And the first stage to my reaction is I have to compress this down to a high enough pressure. You'll learn the conditions in about 2 minutes. I'm going to go over some of the conditions for this reaction. And after a compressor, it's sent into a reactor, and the reactor happens on a ion catalyst. That's something that you need to remember about this reaction before finally going through a condenser. Now, what you need to remember as well is that ammonia has a lower boiling point than hydrogen and nitrogen. So if it's at a lower temperature than the reactor, then what will happen is my ammonia will condense out. Then I will be able to collect my ammonia, and then what I actually do is I pass any unreacted nitrogen and hydrogen, and I put it back into my compressor, and it goes through the reactor again. If I look at my reaction in a bit more detail, what's actually going on at a molecular level, well, I'm reacting nitrogen in its gaseous state with hydrogen also in its gaseous state. And this is a reversible reaction forming ammonia. Now, I'm going to have to balance this reaction dead quickly. There is 2 nitrogens here, there's already 2 nitrogens here, and I'll just put a 3 there, and that is a balanced reaction. Now, because it's a reversible reaction, what you could be asked is the conditions of this reaction, because they're going to follow the same principles that we've already looked at when we looked at Le Chatelier's principle. Now, this reaction is exothermic in the forward direction and endothermic in the backwards direction. Now, if I increase the temperature, then what's going to happen is my endothermic reaction is going to be favored, and I will actually push my reaction to the left. Now, if I look at pressure this time, I will actually make a difference. I've got 4 moles of reactant and only 2 moles of product. So if I increase the pressure, then I will push my reaction to the right. And remember, as this reaction is going on, I'm condensing my ammonia to remove it during the reaction. So I'm actually removing some of my NH3, and that's going to push my reaction to the right. So if you are wanting to get your maximum yield from your Haber process, what you're going to want to do is you're going to want to use a low temperature, high pressure, and remove a lot of your ammonia. Now, there is a key compromise that you have to make in this reaction, and that is the fact that the rate of reaction would be incredibly slow if you did use a low temperature. So in fact, we use a temperature of 450 degrees centigrade, and the reason why we do this is so we have a quick enough rate of our reaction, and we also get a fair yield. Also, I cannot use really high pressures because of the fact I have hydrogen, and hydrogen is a flammable gas. So what I need to do is need to find another compromise, and I pick a pressure of 200 atmosphere pressure, and this means that my reaction gets a good yield without being too dangerous. We're now on the final hurdle, people. We are on our last topic, and we are going to look at NPK fertilizers. And NPK fertilizers, well, it's kind of in the name, are fertilizers containing either nitrogen, phosphorus, or potassium. And these key minerals are vital for a plant. Nitrogen is used by plants to make healthy leaves. Phosphorus helps produce healthy flowers on my plants and also healthy fruit. And potassium is what produces plants' healthy roots. Now, a lot of natural fertilizers like manure and things like that are spread on field. However, what we want to do is we want to be able to control the amount of nitrogen, phosphorus and potassium in order to get the maximum growth from the plant. And for this, what we have to do is use artificial fertilizers, which will be produced in a laboratory. Now, what is also important to remember about these artificial fertilizers is they need to be able to dissolve into the soil. So they often contain NH4 plus ions, NO3 minus ions, or PO4 3 minus ions in order to make sure the fact they can dissolve into the water and the soil. Now, we can make fertilizer in the laboratory as well as on an industrial scale, and there is advantages and disadvantages of doing both of this. You might have made some fertilizer in school, I don't know, but a quick advantage of making fertilizer in a laboratory is the fact that when you do this, you're using pretty cheap apparatus. And if you look here, we actually have a laboratory setup that you would use to make fertilizer in school. Just a simple titration. You'd be reacting something like nitric acid with an ammonium compound in order to make your fertilizer. Now, when you do this reaction, it is going to give out a bit of heat. And because of this, doing it in a laboratory is a bit easier to control. It's not going to be as exothermic, give out as much heat as if you would do it on an industrial level. So this is going to be a safer way of doing this because it is going to be less exothermic. But on the contrary, we do have a few disadvantages of carrying this out in a laboratory. It's going to be an incredibly long process because you'll have to carry out crystallization, which can take a long time in order to dry your fertilizer and make sure that it's crystallized well enough. Also, you're going to make your product in pretty low concentration. So this method of producing fertilizer is not what we use on a large scale. What we do instead is we use the industrial way of producing fertilizer, and this has the advantages of being able to produce things on a much higher scale, and it's going to have a lot higher yield, and you're also going to get a much higher concentration product. Also, if you look at the industrial process, it's going to be quite quick. But we do have disadvantages of the industrial process. The industrial process might be quicker, but it is a lot more dangerous. You are going to be having a very exothermic reaction, which could cause really quite bad explosions. And as well as this, we are going to be working with very expensive equipment, and it is a lot more complex and a lot more stages involved. Now, I really hope you enjoyed today's video. This is something that takes me quite a lot of time to make these videos, so I really would appreciate if you subscribe to the channel and drop it a like if you found it useful. Thank you for your time and best of wishes with your Chemistry Paper 2 exam.